Hi everyone, my name is Nicole Stott and I'm a flight engineer with Expedition 20 on the International Space Station. And we're here today with you on the International Space Station and the Japanese Laboratory Module.
Hi, I'm Bob Thirsk. I'm also a flight engineer aboard Expedition 20. The topic for today is weight versus mass, a heavy-duty concept.
So what is weight? Weight is the vertical force exerted by a mass as a result of gravity. Weight also means the strength of the gravitational pull on the object. That is, how heavy is it? Weight is dependent on gravity.
On Earth, in a 1G environment, an astronaut in his spacesuit would weigh 360 pounds. On the Moon, in 1/6 Earth's gravity, the astronaut would weigh 60 pounds. In orbit, he would weigh 0 pounds because weight is dependent on gravity and the effect of Earth's gravity is not observed.
Using more physics and mathematical terms, weight is defined as the force with which a body is attracted to Earth or another celestial body, equal to the product of the object's mass and the acceleration of gravity. So in equation form, gravity equals mass times acceleration due to gravity. On Earth, that's 9.8 meters per second squared.
But what is mass? Mass is the property of a body that causes it to have weight in a gravitational field. The mass of an object is not dependent on gravity. Mass is the amount of matter in an object. Bodies with greater mass are accelerated less by the same force.
If we use the same force on these two animals, the elephant, which has a greater mass, is affected less than the mouse, which has much less mass.
And what is gravity? Gravity is a force that governs motion throughout the universe. It holds us to the ground. It keeps the moon and the station in orbit around the Earth, and the Earth in orbit around the sun. It is best described as the attraction between any two masses, most apparent when one mass is very large, like the Earth. The acceleration of an object toward the ground caused by gravity alone near the surface of the Earth is called normal gravity, or 1G. This acceleration is equal to 9.8 meters per second squared, or 32.2 feet per second squared. If you drop an apple on Earth, it falls at 1G. If an astronaut on the space station drops an apple, it falls too. It just doesn't look like it's falling. That's because they're all falling together. The apple, or the onion, the astronaut, and the space station, all falling together.
Well, what is microgravity? The International Space Station and us astronauts aboard are traveling at approximately 28,000 kilometers per hour, or 17,500 miles per hour. And we're essentially falling around the Earth, creating weightlessness. The weightlessness that is felt in free fall on a ride at an amusement park or on the International Space Station when it circles around the Earth is microgravity. Objects in a state of free fall in orbit are said to be weightless. The object's mass is the same, but their weight would register 0 on a scale. Weight varies depending on if you're on Earth, the Moon, or in orbit, but your mass always stays the same. The first thing that Koichi and I would like to do is demonstrate that we're actually on board the International Space Station and we're in a weightless environment. So let us show you a few little tricks here that will make that point. I'd like to have an arm wrestle with Koichi. Let's see what happens.
This is great, actually.
One of my favorite Japanese sports is sumo wrestling. We're going to try to sumo wrestle.
The somersault.
Okay, Nicole, show us your stuff. Where'd she go?
Oh no!
Come back. It's Superwoman.